Okay. Okay. Yeah, I will monitor. I will try to keep an eye on the on the Q&A. What I'm going to briefly introduce now is the ability to model antenna arrays. So antenna arrays, they are used in radar, in wireless, in satellites. So it's something quite generic. What I just want to show a few things here. What do we want to do? Define an array. So an array, it's a combination of multiple radiating elements in a specific geometry. We want to take into account potentially mutual coupling. So we've got different approach. We can do without, which is going to provide a kind of theoretical result, and we can go a little bit more in depth and model this mutual coupling. Signal processing like beamforming, interference mitigation. We may want to define a zone where there will be very little gain, so that we can avoid an interferer or things like that. Calibration is of interest as well. Waveform design, that was mostly for radar. I'm going to skip this. But basically here, the first toolbox I'm going to talk about is called phased array toolbox. And phased array toolbox provides the ability to define different geometries in 2Ds, linear arrays, rectangular arrays, or in 3D, something a little more complex like this. And so you will be able to define the geometry, and from this geometry define what is the antenna radiating pattern, what happens when I steer my antenna on the left, on the right, up, down, whatever, and also go a step further and define some beamforming algorithm. So we provide a few so that you can define and do something a little bit more dynamic in your scenario. So the first tool I'm talking about is the phased array toolbox. So the phased array toolbox is using a simple approach, meaning that I define radiation pattern for each of my element, and I do the combination so that I can get the pattern. So I'm not taking into account mutual coupling. I'm not taking into account, what happens here compared to what happens here. It's something I consider the radiation pattern for each element, and then I compute the resulting using superposition theory. So, and what we do is we provide some predefined custom geometries, the most widely used ones, so that within a few lines of code, you can again define your geometry, extract your radiation pattern, and use that and steer the beam and use that in your scenario. The next tool, which is the complement of the phased array, is the antenna toolbox. So the antenna toolbox provides a solver, an electromagnetic solver. So here we provide a set of geometries, predefined geometries that you can adjust. So you've got a catalog of antenna, you can adjust the size, the number of elements, and so on. And then here, it's going to use an actual electromagnetic solver to get the radiation pattern from the antenna. Of course, this is going to take more time. So you need a larger computer. you need to have a little bit more time. But what it brings is the ability to have a pattern that is going to be more closely matching the reality. So we can go, first step with phased array toolbox and define the weights for the steering parameters and so on. And then if you really want to have a very, very fine analysis, we can complement this using the antenna toolbox. So there are several use cases, and I'm just going to talk about a few and show you a tool just so that you can have an idea. Here, I just wanted to spend little time, but to tell you that we can define the satellite scenario. We can attach antenna or antenna arrays that are really customized. So here we may want to do knurling. So here I've got an interference. I want to knurl the antenna in this direction so that it's not generating too much problem. So this is one of the use case. Windowing is trying to make sure that we're going to avoid these side lobes and minimize the side lobes. So we've got functions to do that, and we can synthesize. We've got some examples that show how to synthesize a pattern you would like to achieve, and see how you can do that using MATLAB with the optimization, with artificial intelligence, more and more deep learning. And here another thing is the problem with this large arrays is that it requires a lot of radiating element. It requires a lot of modules, electronics behind that to process. So here there is something called thinning, and see how many of these radiating element can I remove. And of course it removes weight, it removes consumption, it removes electronics, so it reduces a little bit the cost, and still keep proper radiation pattern, proper performances. So a few of the use cases that are available. Well, I had a few slides. I didn't remember. I had a few slides. Optimization and AI for pattern synthesis. These are two workflows we are documenting pretty exhaustively in this toolbox, because this is very highly in high demand these days. So here the goal is to define, okay, I want to maximize I've got a specification. I want to maximize directivity. I want to make sure I suppress the interference by at least 30 dB. I want to keep any side lobes below minus 17 dB. So this is just an example. And then we show how to use known regular optimization techniques to do so, and use deep learning to also achieve this kind of solution. So this is a shipping example, and I will share my slides, and you have all these links here at the bottom. The next thing is, we want to be able to do some beamforming, so define exactly without any mechanical action where to focus my beam. We also could be interested in estimate the direction of arrival so that we can, steer to the actual source of the signal. And in this toolbox, in phased array toolbox, we provide the most widely used and known algorithms. So basic beam scan, the Capon, which is the MBDR, music, Esprit, and so on. And so we define, you can use those algorithms on linear, rectangular, or arbitrary geometry. So here we just show which one works well with which geometry, and there are also additional techniques for wideband. So this is out of the box, again, with examples to show you how to use those tools. If you want to learn more, we also provide a set of introduction videos. So here it's really to understand how things work. So if you already are familiar with those topics, this is probably going to be a bit basic. But if you've got new employees, young engineers who are not totally familiar with that, it can, explain a little bit, allow them to understand how things work, and then go into MATLAB and experiment. Just in a very, 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 very limited time, what I want to show you is, again, here I'm just going to scratch the surface, but there is an application that is called the Sensor Array Analyzer. I just want to show you this. Oh, here, move it here again, up. Interactive application. Just to recap what we've seen with the antenna arrays. If it wants to start, okay, come on. Okay. Interactive application, start on top left and go to the top right. So here we've got a catalog of 2D arrays and 3D arrays you can choose from. I'm gonna stay with the linear because it's fast and easy to understand. You can define, for instance, the number of elements. I don't want 4 elements, but 8 elements. They are all spaced by 0.5 lambda. My propagation speed. So this is a generic tool. It can work with hydrophones. It can work with microphones. It works for antenna. So that's the reason why you have to specify the propagation speed. And let's say my signal frequency is 2.4 gigahertz. So here it's just going to give me the geometry. It's going to provide some details here. At 2.4 gig, I can expect 12 dBi when I'm steering at 0, 0. There are tools to replicate, partition. We can, have subarrays and things like that. I'm not going to go into the details. The next big thing is you can select the radiation diagram of each of your antenna. So here I'm going to leave it as an isotropic, which is, default. And then with one button here, I can get my 3D pattern estimation. So again, this is purely mathematical superposition. So that's the reason why it looks really so clean and symmetrical and whatever. I can specify the steering. Let's say I want to steer at 32 degrees. So I'm going to see the effect on my radiation pattern. So that's what happens when I'm steering at 32 degrees. Of course, the 3D looks good, but most of the time we will be working with 2D patterns, which are easier to understand. So here, that's what, if I'm asking 32 degrees, that's what the radiation pattern is going to look like, and so on and so forth. Different type of visualization. I can define I can visualize in polar or rectangular coordinates and so on and so forth, and a few other things. I'm not going to go into the complete description, but here, same thing. I can generate to MATLAB script, and it shows me how to do that. So I create a uniform linear array, 8 elements, spacing in between the elements. Each element is an isotropic antenna. I'm working at 2.4 gig. Propagation speed is speed of light, and so on and so forth. And I can plot and I can visualize and I can steer. So it shows me also here how to create the steering vector. There is an object phase steering vector that is gonna return the weights I need to apply on each of my antenna elements. So what is the phase and the amplitude I need to apply on each of these elements to steer my beam in the right direction. So easy way to get started. This toolbox does much more than that. Beamforming, estimation of arrival, direction of arrival estimation. So many more things, but I just wanted to quickly talk about it so that you can realize that we can also add that on top of the satellite communication toolbox. And finally, and here again, I'm just gonna go just give you a quick overview, because this topic can be the focus for a complete session. We've been doing simulation. Okay, MATLAB, Simulink, we know that that's exactly what it's been for. We've got some options to connect to some instruments and grab data into MATLAB and do some rapid prototyping. That's what we call radio I/O. But eventually, you probably also would be interested in generating code. So take your algorithms and make sure you can embed those codes into an embedded target. And so this is what we address with software-defined radio. So software-defined radio, there are software-defined radios like the Blade RF, the ARC RF, the USRPs, low-cost modules that you can use for quick test or evaluation in the lab. But that's not what I'm going to be focusing on. I'm going to talk more about the FPGA and the SoC board. So again, the very, very high-level overview is we do the modeling in MATLAB Simulink. So this is what we've been discussing so far. We've been providing some capabilities, ability to connect to USRP radios or Pluto radios from analog devices, so that the radio is just here to grab data, over-the-air data, and so you can do all the processing in MATLAB. This is what we call radio I/O at MathWorks. So this is easy way to test your signal, to test your TX, RX, your complete system in the lab, for instance, with actual hardware, and just see if, you know, there is not something that you could have been missing in your design. Sometimes simulation you can always make it work, but when you connect to the real world, things in general are a little bit more complex. So this is the easy way. And then the next step is the ability to take your model. So there is a workflow where we go from MATLAB to Simulink, and we make our Simulink model what we call hardware friendly. So we make it using fixed point rather than floating point, so that we can take advantage of CPUs or the FPGA, and in general it's both. We make sure that we use streaming. I was, you know, briefly talking about streaming, but an FPGA, it gets one sample at a time. So we need to think our algorithm so that it can process in this way. But we've got workflow, we've got examples, we've got reference applications that show you how to do that. So in this case, you've got the transceiver, you've got the signal processing is done on the CPU or on the FPGA, on the SoC, and then we still have the ability to get a communication channel with MATLAB and Simulink so that we can, you know, do all the test and verification, grab data from the processing, making sure that we can, you know, look at the memory elements and see if things are going right, and then we can deploy in a standalone application. There is a workflow, but what I'm going to show you instead, because we've got just a few minutes left, I'm just going to show you the most emblematic tool that we provide in this direction. So here in FPGA, ASIC, and SoC, we've got a toolbox that is called Wireless HDL Toolbox. So Wireless HDL Toolbox provides HDL optimized blocks so that we can apply to 5G, LTE, satellite, WLAN, and so on. So of course, I'm just going to focus on satellite communication. So right now, what we've been providing is, for instance, this GPS reference application overview. So here we explain a little bit, you know, how to implement what is a GPS a receiver. So GPS receiver is a bit tricky because you need to capture multiple satellites, and there is a spread spectrum so that we can then tell which one is which. So it's not necessarily a very easy way, but what we provide is reference application. So let me go back here. Reference applications that help you get started. For instance, if I want to implement a DVB-S to HDL receiver, I've got something that is working out of the box. DVB-S to HDL transmitter, I've got something. So here, when I say we've got something, it's a complete solution. Let me go down a little bit. So here we've got the different building blocks. So here we are not in MATLAB anymore. We are moving to Simulink for different reasons, but mostly to be as close as possible to the hardware implementation. It makes things much easier to do that in Simulink. We've been optimizing our tools. We've been developing more features in Simulink to do this type of application. So that's the reason why here you're going to see mostly blocks. Each block here is a high-level function, which is comprised of more advanced blocks inside. Let's say the FEC encoder here. So we've got an LDPC encoder. So we've got, again, it's slightly more advanced. We are talking about generating code on an FPGA that is running at a very high sample rate, where the delays need to be taken into account, where the optimization can require you to pipeline and do all these kind of things. So that's the reason why I just want to show you it's existing. If you want to build a prototype, if you do not have the team for HDL, FPGA programming available at the specific time, there may be some in between. Here again, if you want to do something that works really efficiently, you still need to have hardware skills. You need to know how to optimize your model here to take advantage of the features on your FPGA. This is something we've got training for. This is something that we are heavily working on because, you know, starting with a reference application that is, you know, well designed, well defined can help you save a lot of time, and this is something we've been heavily working on. The beauty of it, I will not be able to show the whole thing today. Again, if this is something of interest, please let us know. We can organize a dedicated session. But the beauty of it is all these blocks, they generate code that you can read. It's not a black block that is, you know, impossible to read. It's code that is documented. We've got some estimation of the resource for each of these blocks, so you can tell, okay, is it going to fit? Is there a chance it's going to fit on my target or not? We can generate the HDL code and the C code, and there is a communication in between. So yeah, this is something that once you've got a baseline can really help you save a lot of time, because you focus on the model, you focus on the algorithm, you focus on the design, and then the code generation is automated. So, but I don't want to make you believe it's something that is easy and I press the button and it's going to generate something. There is a complete workflow. It remains hardware. As soon as we go on hardware, especially with this type of highly demanding application, we need to be careful. But we provide this path. What else? I probably have a few more slides, but I'm not gonna go into the details. Just to conclude with this, yeah, this implementation, what is interesting is that we've got tools to facilitate the conversion from floating point to fixed point. Here, depending on the target, you know, MATLAB Simulink, you can tell, okay, this is the limits of the signal I want to use. It's going to propose you some fixed point configuration that makes sense, and you will be able to optimize with an iteration process that we describe clearly. It's going to generate code. It's going to be very easy to use the scripts, the initial models, to verify that, you know, your bit accurate, that everything is running as expected. So this is what we are really focusing on, making sure that we can provide an end-to-end solution. The different software-defined radio we support, again, we need to make sure we understand what is radio I/O. So this is just, you know, grabbing data and do the processing in MATLAB. So here we've got some low-cost radio like this Pluto. We support the RFS, some Z-board with the analog device transceivers. And of course, the big thing today is the RF SoC, which is really going very, very high in frequency and provides some very interesting features. Again, I just wanted to show you that, you know, we've got this reference application. It's not just in MATLAB. We can go to the implementation. This whole topic may require a dedicated session. So if this is something of interest, yeah, please do not hesitate to let us know, and we will be able to organize a session to talk about that in more depth. That's all I wanted to talk about. It's it's almost 2:30, so I don't know if there are a few questions. If we've got time for a few questions.